Thank you for having me. I'm very excited to talk about dark matter with you all and black holes, and what specifically we will talk about is collapsing galaxies, creating black holes with dark matter at cosmic dawn. So typically when we think of the universe, we think about, like, when we think of the cosmos, we think about the really bright and beautiful things like stars, galaxies, and nebulae. But it turns out there's actually a lot more dark things or invisible things in the universe, like black holes riddle galaxies. Every massive galaxy, including our own, seems to have a supermassive black hole in its center. And although you look at this sort of this Hubble deep field, where you see just galaxies, they're actually shrouded in dark matter. So there's a lot more to the universe than meets the eye. A lot of it is dark. Now, one thing that I'm going to address today is what the connection between dark matter and supermassive black holes could be. And today I'm going to show you exactly what that is, how we have two really pressing questions. One of the things that we don't understand at all is how these supermassive black holes formed, because we find them very early in the universe. And so if the whole point of this work that I do would help us answer two of the most pressing questions in cosmology: what is dark matter, and how are supermassive black holes formed so early in the universe's history? So let's start with talking about what black holes are. And essentially what black holes are is what happens in space-time when you take too much mass and cram it into a really tiny space. At that point, because mass interacts with gravity, the gravitational force there is going to be so immense that it will create a collapse into a never-ending collapse, leaving something behind called a black hole. And black holes their gravity is just so strong that nothing can escape it, not even light. And light is the thing that travels the fastest, as we know. Nothing travels faster than light. And they have this thing called a Schwarzchild radius, which you may have heard of as an event horizon, and that's the point of no return. So if you get too close to that, you cross the event horizon, it's done. Like you're falling in. You're essentially out of this universe. And the reason why I give this equation, it doesn't really matter, but it's because I have done some cute calculations here with the Schwarzschild radius of my hamsters. So using this calculation, and this is Charmini, she's named after the charm quark. I named my hamsters after subatomic particles, and this is Muini, named after the muon, and those are their masses in grams. So when I calculate their Schwarzschild radius, if you were to turn like a black hole out of that kind of mass, it's really tiny. It's like 10 to the minus 29 meters. So and let's compare that to the size of an atom. Excuse me, the atomic nucleus. Atomic nucleus is 10 to the minus 15 meters, which is far larger than this. So their Schwarzschild radii would be extremely small, or their event horizon. So, okay, I also calculated some for other objects like the Earth and the Sun. You get some more reasonable things, but I want to turn your attention to this incredible object, which it's called TON 618. Maybe it's TON 618, I'm not sure. But this is the most massive black hole that we have observed in the entire universe ever to this date. It weighs 66 billion suns, 66 billion. And this, if you calculate its Schwarzschild radius, it's more like 10 to the 14 meters. So that's a 1 followed by 14 zeros. And that's 1,285 times the Earth-Sun distance. In fact, it would be 30 times more far than, or it would engulf the orbit of Pluto. Pluto is 40 astronomical units away, where astronomical units are the Earth-Sun distance. That's what we just call that, an astronomical unit. So essentially that's just saying that like Pluto is 40 times farther away from the sun than the Earth is. And so it would swallow that orbit 30 times over. So we really wouldn't want to replace our sun with this black hole, that's for sure. But it's just incredible to think that there's something like so massive out there. So here I'm going to talk about, I'm just going to tell you a little bit about what kinds of black holes that we have. So stellar mass black holes are black holes that are left over after the death throes of a star. So when a star ends its life, that's really massive. So the more massive stars, the most massive ones, they explode into supernova, and then they end up collapsing in on themselves because the gravity, there's too much mass there. So the gravity takes over, and then it collapses back into itself and leaves a black hole behind. And these exist basically anywhere that there are stars. So the masses of these, I say less than 100 solar masses, but it's really a lot less than that. Like, I think now the largest black hole that a star can create would be more like 50 or something like that solar masses. But I'm a cosmologist, and order of magnitudes are what we use. So less than 100, it works. Then there are intermediate black holes, which are actually very important. Intermediate mass black holes are black holes that could, form from like accretion. So when I say accretion, I mean like eating. So when black holes eat, they're accreting matter. They form through merger. So that's the stuff that we see from LIGO when they discover like two black holes colliding and merging. And these exist throughout every galaxy, and maybe in the center of smaller galaxies as well. These would be up to about 100,000 times the mass of the sun. And these are really important because they're kind of the key to explaining the formation of supermassive black holes. They sit at the center of every galaxy, but we have no idea how they formed. No idea, really. Okay. Well, we have some ideas, of course. This is what I'm doing, but we just don't know. Like, conventional methods cannot form such a massive black hole in the time that we see them. And so these are going to be like millions to billions of times the mass of the sun. The one in the center of our galaxy is 4 million times the mass of the sun, compared to the one that I just showed you, which was 66 billion times the mass of the sun. And this one here, I think, is 6.5 billion times the mass of the sun. M87, which is our first image of a black hole. So one question some people might ask is like, what's inside a black hole? What is it? Does it connect two regions of space? So kind of like a wormhole? Like, is it a shortcut through space-time? Do they hold entire universes inside them? Are they places that you can transcend time and go and tell your daughter about what you saw in the black hole so that she can solve the gravity equation like Coop did in Interstellar? We don't really know. We don't know what's inside, because once you cross the event horizon, that's it. There's no communication with the outside world. And so that's where Interstellar gets a little bit creative, because he is communicating in some way with somebody, with his daughter from inside the black hole. One thing that I do know, and one thing that you should know, is that if you were to go into a black hole, you would not want to go into a stellar mass black hole. That's because its event horizon, remember the event horizon, the Schwarzchild radius gets larger with larger mass. So the singularity is going to be a lot closer to the event horizon. So you fall in there and you get spaghettified, you get stretched apart, and that's not fun at all. So what you would want to do is go into a supermassive black hole. The singularity is going to be a lot farther away, and it's safer, and then maybe you can end up in a tesseract like Coop did. But let's ask this question. How do supermassive black holes exist when the universe is so young? So the problem with the supermassive black holes, it's not that we see them around today. It's that we see them as far back as when the universe was only 700 million years old. And there's all the conventional methods that we know of for black holes to grow. They just can't create something like that. So let's say there's something called super Eddington accretion, which is just essentially black holes eating matter at a very, very, very fast rate and perfectly efficiently, meaning that they're continuously eating matter, so they always have a supply to eat. And if you do that from the very early universe, from a stellar mass black hole, and I took a 100 solar mass black hole to make this calculation, I find that it only creates about 100 million solar masses, which is 10 times too small to explain the billion solar mass black holes that we find. So we need seeds that are a lot heavier than just stellar mass black holes. And so it turns out that maybe it's not the light areas that you want to look to for this answer. It might be actually something that we can't see that exists everywhere and serves as the glue holding galaxies together and formed the pattern and the shape for what the universe looks like today. Then that's dark matter. We know it exists with various we have various pieces of evidence, and the most popular one is going to be rotation curves. And what rotation curves are essentially, it's just if you take like stars and you plot their velocities from the center all the way out to the edge of a galaxy. So you take that, you plot its velocity with respect to how far away it is from the center, and you get this sort of a curve. Now, what we expect would be something, could be, we have a very good understanding of gravity, and we have like a giant cosmic lab in our own neighborhood, which is the solar system. So we see that in the solar system, the farther an object is away from the sun, where the sun is the central mass of the solar system, like none of the other masses matter compared to the sun. The sun is like the mass of the solar system. So the farther away a planet is, the slower it moves around the sun. So Mercury moves faster than Venus, Venus moves faster than Earth, Jupiter moves faster than Saturn, and so on and so forth. And so if you were to take, we would expect to see a similar thing in a disk galaxy. And so when we take that and we plot that rotation curve, we would expect to see something that looks like this, where your speed is decreasing the farther away that you are from the central mass. However, Vera Rubin in the late 1960s with Kent Ford, when she looked at the Andromeda galaxy and checked its rotation curves, she found that all the speeds are pretty much constant. They're almost the same, even at the edge. So if you take all the matter that we can see, so all the stars and the gas, and even if you include black holes and brown dwarfs, which are stars are failed stars, so stars that didn't have enough mass to start fusing, and so you can't really see them. So even when you add all that stuff in, there's no way that this galaxy could be holding together. No way that galaxies could hold themselves together at that speed. So the more massive an object is, the more it kind of creates a potential, a gravitational potential, which is like a bowl. So the more massive an object is, the deeper that potential well is. And all the mass that we can see, and along with black holes and all that stuff, creates a potential well that's way too small to be able to hold galaxies moving this fast. And so there has to be something that's holding them together. Galaxy clusters are similar, and this is from Fritz Zwicky actually found in the Coma cluster in the 1930s that it looks like that things were moving way too fast for the galaxy to be held together. Now at that time, they didn't really know how much gas there was and all that, so he overestimated the amount of dark matter in galaxy clusters by a lot. However, here's what we know. A really key thing that, and the gas is important, because a key thing about galaxy clusters is that most of its mass is actually in gas. So there's 10 times more mass in gas than there is stars. And so even when we take that into account and see what kind of gravitational potential well you get, it's still too small to hold galaxy clusters together at the speeds that galaxies are moving in them. Now here's a pretty famous cluster. It's called the Bullet Cluster, and they call it a smoking gun for dark matter for the following reason. So let's talk about what the Bullet Cluster is. The Bullet Cluster is a cluster of two galaxy clusters that have already collided with each other and passed through each other. So this is like the larger cluster over here, and this is the smaller cluster over here. So these have already passed through each other. they've already collided. The gas is important again, because there is 10 times more gas than there is dark matter, than there is, excuse me, there's 10 times more gas than there is stars in galaxy clusters. And so in this picture, they kind of put like this blue region around here where it's just the stars, and they color the gas in pink. And this is actual data. When stars, so when a cluster or two clusters of galaxies collide together, generally you're not going to experience any interactions between the galaxies, because there's so much more space between the galaxies than there is the chance of actually colliding with another galaxy is so small that it's just kind of like essentially they just don't interact. Similar thing's going to happen when Andromeda and Milky Way collide, by the way. There's a lot more space than you think in between the stars in our galaxies. So for the most part, the stars are not going to interact. So that's the key thing. So the stars, the galaxies, they'll just pass through each other without any interaction. The gas, however, not the same. Gas will experience drag. So if you were to take two clouds of gas and smash them together, they couldn't just go through each other. They would interact and hit each other and bump around like particles in them, and then kind of move through. So the drag that it experiences would cause it to be left by in the center. And this is why we see all the gas kind of here, because it's been dragged behind with the interactions that it experienced with the other gas cloud in the galaxy cluster. And so since gas is 10 times, there's 10 times more gas mass in galaxy clusters than there are stars, if we plot that potential well that I was talking about, so like where your gravitational potential well is like a bowl, and the more massive you are, the deeper that bowl is going to be. If we plot that, we should see that the gravitational potential is essentially dominated over here, because that's 10 times more mass than the stars. But when we plot it, we actually find that the gravitational potential wells are in the regions where the stars are. So the more massive regions are where the stars are, which are only 10% of the mass in gas. So there must be something else that also doesn't interact, and that is dark matter. But there's another thing. Gravitational lenses. I love these. So these are just essentially, they're proof of Einstein's theory of general relativity, which says that mass bends space-time. Newtonian physics didn't say that. So, but when Einstein came around, he said that when you put a mass on in space-time, it will bend in the same way that you were, let's say you took a bowling ball and put it on your bed, on your mattress, it would bend inward too. Of course, it's in 3 dimensions, so it's a little bit different, but this is kind of like an analogy that I like to use. And what they are is that they kind of almost like they're like magnifying glasses that allow us to see things that are very, very far away. So this galaxy, this is a galaxy that you see here. This is actually behind this galaxy cluster and very, very distant. And if space-time was not bent by mass, then we wouldn't even see it. It would just be blocked out, you know, in the same way that if you put like something behind your couch or whatever, you won't see it, right? And that's because, you know, I mean, everything has a gravitational potential, but the couch is a very small piece of thing, whereas the galaxy clusters are incredibly massive. They could be like 10 to the 15 times the mass of 10 to the 15. So 1 followed by 15 zeros times the mass of the sun. They can have that much mass in them. And so because space-time is bent, you find that the light that galaxy emits kind of just circles around it and creates these arcs. And if you have a perfect galaxy cluster or a perfect lens, so like it's like if the galaxy is perfectly centered right behind the galaxy cluster that is lensing it, you would find like an entire ring. And it's very rare, but it happens. And that's called an Einstein ring. So with that, it's an Einstein ring. And with that, we can actually take the size of it and measure how much mass is creating it. And you guessed it, even when we account for the gas and all the stars in there, there's no way that you can get a gravitational lens this big. Now, one of my favorite pieces of evidence is a baby picture of the universe. It's a cosmic microwave background. So this is just when the universe was only 400,000 years old. Beyond the cosmic microwave background, you can't see anything. It's opaque. The universe at that time, the universe is expanding and accelerating, so it's growing. And back when it was smaller, everything was a lot more dense. So like matter and photons and all that were very close to each other. It was very hot, like a plasma soup. So and it's kind of like opaque in the same in a similar way as you can't see through the sun. So we can't see invisible light beyond the cosmic microwave background. But it imprints stuff for us. It kind of imprints stuff for us and shows us how matter is distributed. So going back to this point where where matter and photons are interacting with each other, because everything is so densely packed together, everything is just bouncing apart. And so it leads to this this sort of like these features that we see. So like one thing I guess I want to explain here is that the blue areas are denser than the red areas. And when I say denser, so it's like the universe wasn't exactly uniform in the early universe. It had these tiny little density fluctuations where the blue regions are more dense than the red. But when I say more dense, I mean like 1 part in 100,000. Otherwise, it's pretty smooth. So it's generally smooth, but these fluctuations they matter a lot, because that's because you had these sort of density fluctuations or little potential wells. Matter interacts with gravity, so it would want to fall in. Now, regular matter, it's kind of represented by these orange balls here, interacts with photons. We know that because, well, we could see each other and all that. So way back when the universe was so hot and dense and everything was bouncing off of each other, and photons would bounce off of everything else, there's photon radiation pressure, which would push the matter that falls into this gravitational well, it would push it out. So matter would try to fall in under gravity, but because it interacts with photons, photon radiation pressure pushed it out and wouldn't let it do that. However, dark matter came in there and it was just totally fine. It didn't even see the photons at all, and it just kind of coalesced and it formed the seeds for everything, the stars and the galaxies that we see today, creating this giant cosmic web. And so this is like a piece of art from a project that I did with my friend and brilliant artist Catherine Machen. This is a cosmic web of dark matter. So we did this sort of like a project where she painted my work, and so the sort of so the sort of like these little density fluctuations that you see translate to creating this cosmic web of dark matter, where the more dense regions are going to have more stuff in it. So like the more dense regions would have lots of matter in it, and it would correspond to like where the galaxies are today, galaxies and galaxy clusters. And this is a very important thing, because the universe had to have had that happen very early. It couldn't have waited until 400,000 years after the Big Bang, because by then you wouldn't get the large scale structures that you see today if it was just with normal matter. So it's a vital part of that story that there's dark matter there to create this cosmic web. Now, this is a simulation. So kind of like what we were looking at in that painting was maybe like a swath like this. This is like a larger scale, but it's from a simulation. However, there is data from the Sloan Digital Sky Survey that actually shows us, like when you look at the universe, right, as kind of like from zoomed in, you don't see much of like a pattern like that. But when you zoom out and you zoom out really far away, you start to see that there is this interesting looking like web. So this is actually in the data, and I want to mention that like you're going to see like a couple of regions where there's like just no data there. That's because we live in a disk galaxy, so some of our view is blocked. But everything else, look at that. It's a perfect cosmic web. And the really beautiful thing about this is like it corresponds actually to where the cosmic microwave background shows us it. So it corresponds to the density fluctuations that we see encoded in the cosmic web. So it's I love this. It's just wonderful. And this is something you actually you absolutely need dark matter for. And the reason I guess why I asked why we had the poll about like to see whether people think it's dark matter or gravity or whatever is because one thing I want to get out there is that modified Newtonian dynamics is not going to do it because Newtonian gravity can't even explain gravitational lensing. Okay, so that's just I'm gonna lay that right out there. If you're going to modify gravity, you're going to have to start with Einstein's equations because you have to at least be able to explain what it can explain that we see. And so even if I'm not even saying that we have a perfect picture of gravity, it might change in the future. But even if that happens, even with modified gravity, you need dark matter. It's just required. It's required. It's encoded into the universe itself. So then the question is, when I say dark matter probably exists, I really mean that it almost definitely exists. The question though remains, like, what is it? And that we really don't know. And this is from so there's Daniel White is actually a professor at my school, and Jorge Cham is like the PhD comics person. He does like the art, and they had a book. They made a book together, and this is one of the animations or little I guess art sketches from it that I really like because it's so true. We have no idea what dark matter is, but there are some things that we do know. We know that it doesn't interact with light or regular matter because we can't see it. So it doesn't interact with the electromagnetic force. It does interact with gravity, luckily for us, because that's how we are able to detect it in the way that galaxies move and all the pieces of evidence that I just mentioned. The most important being large scale structure and the cosmic microwave background. We also know that it must be cold, and when we say cold, when we refer to dark matter, we really are talking about how fast it's moving. Is it moving relativistically? Relativistic would be close to the speed of light. That's hot. Whereas something moving slow would be cold. And so it needs to be cold because when things move really fast, so like hot gases, for example, would have a lot more trouble coalescing than a colder gas would, and it would need to be cold by that time in order to be able to form the seeds for the stars and galaxies that we see today and the giant cosmic web. So it might seem weird, and I want to, but I do want to stress this though. Dark matter is just like regular matter, except it experiences different interactions, and I'm going to talk about kind of that right here. So the standard model is for particle physics it is to particle physics what the periodic table is to chemistry. So it just tells us the most fundamental bits. If you take matter and you break it down to its most fundamental parts, you get these things. So like quarks, for example, quarks come together to make things like protons and neutrons. And these quarks are held together by the strong force, which is mediated by this gluon. And yes, these are all my little hamsters that I've named after my particles, or that I've named after subatomic particles. And so I'm very proud of this slide. And then we have the photon is the particle that mediates the electromagnetic force. And then Z and W bosons are the weak force, where weak force is like decays, so radioactive decays, the way that we date rocks and the Earth, for example. And in those interactions, you get like, so muon is actually it's like a more massive version of the electron, kind of. And from those interactions, you get neutrinos, and that's neutrini, and you'll see that he's in 3 spots. And the reason for that is because neutrinos oscillate between 3 flavors, so he could be either one of them. And of course, then there's the Higgs, which is the particle that kind of gives mass to everything. When I said that when I said that dark matter is the same as regular matter, and I wanted to stress that, what I mean is the only difference that they have between each other is that dark matter doesn't interact with these bosons. So these interaction, so they just don't interact with the same particles. They don't interact via the same force, which is why we can't see it. It does interact with gravity, of course, but the graviton is something that's not predicted by the standard model. So but Gravitini, my hamster there, would probably say that yes, gravitons exist. So we don't know if they do or not, though. And so these are possible dark matter particles as well. And again, so the difference between the dark matter particles and standard model particles are that they interact differently. So like if dark matter does interact with something, it might be a different force that we don't know. Now again, so cold dark matter, when we say that, we actually mean cold collisionless dark matter. So dark matter that doesn't interact with other dark matter particles at all. Like it doesn't see other dark matter particles at all. Imagine like taking two billiard balls and throwing them towards each other and they just pass through each other. That's essentially what cold collisionless dark matter is. And that's the standard sort of paradigm of dark matter. But what we find is that it explains it. Look, the cold dark matter paradigm, it explains the large scale structure in the universe as a whole very well. It reproduces it. The problems come when we zoom in and we look at the smaller galaxies, the dwarf galaxies, like these two satellite galaxies of Andromeda. Cold dark matter in simulations will produce dwarf galaxies that have too much matter in their center compared to what our observations tell us. And so one way to get around that is I kind of, I asked the question, or I asked the question that what if dark matter particles will interact with each other? So what if they do scatter? No, what if they don't just pass through each other, like and act like actual billiard balls and just kind of, scatter off of each other via some unknown dark force? And that turns galaxies into giant cosmic particle colliders that we can test dark matter interactions on at various velocities, because we have different galaxy scales. So there's the dwarf galaxies, which are less massive, spiral galaxies, which are more massive, and then galaxy clusters. There's also elliptical galaxies and stuff like that. But the whole point of this is that by the mass, so like the less massive galaxies have speeds in them that are slower than the more massive galaxies are. And because this is actually important that we're able to test it on different scales and with different velocities, because galaxy clusters are pretty happy using just like the cold dark matter model, and they're just fine with it. If you have too much self interactions going on, then it doesn't agree with observations anymore. These two though do, and the way that we can spend, particularly dwarf galaxies, they work very well with self-interacting dark matter. And so self-interacting dark matter would have to have a velocity dependence in a way that if things are moving faster, they are going to be less likely to interact with each other. And that's the kind of velocity dependence the interactions would have to have. Okay, that's all great. So we just talked about black holes and dark matter, but what's the connection of dark matter to black holes? When you turn on the self interactions, something beautiful happens, is that there's this interplay between the interactions themselves and gravity. And this interplay between them is like, so when the central region of a galaxy is always going to be more dense, and so you'll have more interactions happening there. And so when particles scatter off each other, they exchange kinetic energy. So they kind of transfer heat and energy outwards. So particles in the center are losing energy then, kind of, right? They're losing energy, which causes gravity to kind of pull them in more. So they end up eventually becoming more dense. And this thing kind of happens in it's a runaway process that just can't stop once it happens. Because you actually have now particles that are coming in closer that have lost heat to the interactions, and now they're heating up again because they're moving faster. And that can lead to something we call core collapse, leaving behind a black hole that's up to 100 times the mass of the sun. And this is something that can happen in the early universe. So if this happens, that could explain, if we start with like a supermassive black, or excuse me, if we start with an intermediate mass black hole that's 10,000 or 100,000 times the mass of the sun, we can explain supermassive black holes existing in so early in the universe. There are other possibilities too. This one's actually pretty cool. It's called direct collapse black hole. Oh, sorry, yeah, sorry. This is actually another piece of art from that project of mine. It was two black holes that have formed from self-interacting dark matter galaxies that are now merging. But yeah, so the other possibility is this direct collapse black hole. I think it's very cool. It's essentially, you know, it can only happen in the early universe, so it has to be before what astronomers call metals formed, and metals are essentially anything that's heavier than helium. So it has to be at a time where the gas is pristine. It's just like hydrogen and some helium only. And so in the very early universe, since if that's all that it had, what would happen is kind of like you need to have like one galaxy that has a lot of stars that are like radiating energy, and then one galaxy that has a lot of gas sitting next to it, kind of so that it can get irradiated by that energy. The whole point of doing that is that it will prevent it from cooling, and also the fact that you have no metals in it prevents it from cooling. Like for example, today when a gas cloud comes together and clumps together, it will, because of the metals and stuff in it, it breaks apart into smaller little chunks, which is why you don't have really massive stars today, and why stars form in clusters. So like that's why we have star clusters, because they form in the same from the same gas cloud that broke apart due to cooling. And so that's prevented here. And so you have this giant massive gas that doesn't cool, so it just stays together. And so what it does is just kind of like eventually it doesn't, you know, no star, no nothing. It just directly collapses right into a black hole. And this mechanism could also, it could also explain that, because it would form black holes that are about 100 times the mass of the sun as well. It's just that you know the things that you require for it to happen are just so like really, I don't know, like it's really like it's kind of almost like fine tuning. So fine tuning is essentially like when you try to like turn different things, like turn different knobs to make something work. I feel like there's a lot of fine tuning here. There's just a lot of requirements for this to work, but I think it's super cool. And luckily for us, the James Webb Space Telescope's already in space now. It's an infrared telescope, and it's infrared because for two reasons. One, infrared light pierces through cloud and dust, so you can see through that. And two, it will be able to see farther galaxies because the universe is expanding and accelerating. So the expansion is accelerating due to dark energy. There are going to be galaxies that are so far away that, and when that happens, the photons or the wavelength of light that these galaxies emit are being stretched. So the farther galaxies, the ones that we want to look at, which are hopefully around 100 million years, when the universe is 100 million years old, they'll have, due to the expansion of the universe, they'll have a wavelength that has stretched beyond visible light. So like the Hubble telescope can't see that, whereas the James Webb will. And that's how we're going to be looking at the universe at such a young age. It's going to be incredible. We will see like the very first galaxies and stuff like that. And so for me, it'll also be looking at like exoplanets and even stuff in our solar system. So we'll get more of an idea of like Uranus and Neptune, which we haven't even sent any probes to them yet. We only had like the Voyager swing by them. And so they largely remain a mystery to us. But for me, the most interesting thing is looking back as far back into the universe's history as we can, because then, you know, if we see the first galaxies, we might be able to explain that whether self-interacting dark matter can form these black holes, or whether direct collapse is a mechanism to form these intermediate mass black holes, so that we can explain why or how we end up with 1 billion solar mass black holes just 700 million years after the Big Bang. And if it turns out that we do discover that galaxies can, or dark matter, the dark matter in galaxies can do this, can collapse into dark matter, we'll have answered two pressing questions of the universe. One, how do supermassive black holes form so early in the universe's history? And we'll learn more about the nature of dark matter. So we'll learn a bit about what dark matter is. Now, one cool thing I just wanted to sort of throw out there, because we're talking about black holes here too. So in the very distant future, one of the possible mechanisms for how the universe will end is that it's called the heat death. And so in the heat death of the universe, it's not hot, it's actually cold. And what it kind of means is that there's no more heat, there's no more energy to use to do work. So you can't create any more stars, you can't make anything, because entropy reaches a maximum. And entropy is the tendency to for things to become more disordered with time. And once it reaches a maximum, you can't become more disordered anymore, because you've reached your maximum entropy. And so at that point, things and you know, dark energy is stretching the universe apart faster and faster with time, and so it's becoming more dilute. So matters is going to become less important to a point where there's almost only dark energy left. But the one thing that will be left, or that will outlast all of those things, not dark energy. Dark energy is going to be here even when the universe is dead. But the one thing that we'll find that still exists are supermassive black holes, and perhaps ultramassive black holes. And because you could get black holes that collapse from entire galaxy clusters too. And these would take 10 to 100 years. So that's like a 1 followed by 100 zeros. Stellar mass black holes are like 10 to the 70, but supermassive black holes are more like around 10 to the 100 years. So it takes that much time to evaporate in a process called Hawking radiation, where black holes emit radiation and lose mass that way. And so they would be the last things around in the universe before it goes completely black and we're not able to see anything. But luckily we live in the universe that we do today. So let's enjoy it and study it and figure out all the mysteries that it has to offer. Thank you.